Welcome to another Fi-Guy adventure, and we will be converging upon lenses so that we may diverge our understanding from the myths of how they work. So, we will be doing ray diagrams for converging and diverging lenses. Let's jump right into it. What we have is what I like to call a tale of two lenses. Essentially, we're only going to be talking about two of these, but there are multiple lenses actually in that we could talk about. There are converging lenses, which will force the rays of a object once they pass through the lens to converge upon unspecified point up till now. And there are diverging lenses, which, as you can see, there's a couple different shapes of them, which would cause the rays to disperse. And the two lenses that we are going to talk about today are the biconvex lens, otherwise known as the convex-convex or double convex lens, and we will be talking about the biconcave lens, or the concave or double concave lens. And we're going to treat them both at the exact same time. So let's jump into our setup. So we've got our two lenses here. We've got our converging lens on top and our diverging lens on the bottom. So first thing that we need is to show our optical axis, aka the center line. That's the line that cuts through the center horizontally of the lens, so this would be along which we will be showing focal points later on. The second thing that we will need is our center line, because while there is some internal refraction inside the lens, we are treating this with the thin lens formula for how to deal with this, so we will instead be treating them almost as if they are a single line up and down. And that's the best way to treat them. There is, of course, better ways to more accurately represent lenses, but we would need to know the thickness of the individual lens, and then we get into all types of crazy physics, which I don't think you want to deal with just right yet. So we'll start with our basic understanding. The next point is we want to find the adjacent lens side focal point. So if our object is on the left side in each of these top and bottom images, the adjacent lens side would be the side that is closest to us for each of them. Now you're going to notice something when I put this up. The focal points are on opposite sides. Why is that? So if we take a look at this, remember that the focal point is halfway from the center of curvature on mirrors to the mirror itself. If we treat this the same as the lens, we see that the adjacent side for the converging lens is curving around on the right. So the focal point is on the right, and the curvature on the diverging lens is actually curving around to the left. So the focal point for the adjacent side is on the left. Conversely, when we get to the other side, we have the opposite side, lens side focal point. And again, they are both flipped. So this is how our terminology is going to go. It may be different from how I showed you in class, but I'm describing a more general, more complete view of this, which may or may not help you. But the rules will still be the same. You may come up with your own set of rules that are split for the diverging lens and the converging lens. But the rule set that I'm going to give you is going to be a rule set for either one. The thing you have to remember, however, is that the focal point for the adjacent side on a converging lens is on the opposite side of the lens. And the reverse is true for the diverging lens. So let's go to our next one. We can add in our twice the focal points. These aren't necessary, but they're good for showing reference categories, if you would, for where an object starts and where its image ends up. And of course, as I just mentioned, we have to have our very last piece, which is the object itself, which we're going to use a triangle in this case. So let's jump on over to our first rule. Our first rule is that when you have when you're drawing ray diagrams for any lens, you actually both have the first rule is a very nice quick rule, which is any ray through the center of the lens will continue through unchanged. So if we draw that through, it looks exactly the same on both sides. You put it through the exact center, which would be where your vertical lens center line comes in, and your optical axis meet up. Okay, so that gives us one ray, but we need three to figure out where something is and how good we've drawn them. So let's move on to our second one. Our second one is that any ray that intercepts the lens parallel to the optical axis, so it would look like this on the converging lens, will refract in line with the adjacent lens side focal point. So remember, on the converging lens, that's on the opposite side. So if it's in line with it, then it will go straight through it, like this. And we can already see where our image should be ending up over here. But let's look at the diverging side. The diverging side, again, we have it parallel coming in. And when it's parallel coming in, it will be in line with the adjacent lens side focal point, which is this red focal point right here. Now we can't go through it like we did with the converging lens, so we'll have to trace a line from the focal point up to the point where the ray meets the middle of the lens, and then continue our ray along that line. Okay, diverging lenses are much more difficult than converging lenses are in almost every respect, except what they produce. So let's move on to our third rule. Our third rule states that any ray that intercepts the lens in line with the opposite lens side focal point will refract parallel to the optical axis. So this is quick and easy for our converging lens. As before, draw it through the focal point, and then it refracts off in that direction. With our diverging lens, we have to first, because it's not going all the way to the focal point, trace a small, like, little sketch line, or line up your ruler with the focal point is what you should be doing, and draw our ray through to the center only and stop there, because at that point, as the rule says, it will refract parallel to the optical axis like this. So now those are our three rules. Let's go into, well, where is our image? Because the rules are useless without having an image to support them. So if we look for where our image ends up, the image forms where the refracted rays either converge, which would create a real image, which is what we have here on this converging lens over here, or with with where they diverge, such as in this diverging lens here, we have to figure out where the refracted rays appear to diverge from, because they do not converge into a real image. This will make us a virtual image, which if we trace back our refracted lines, they all meet up at this one point right here. So that means that our image will be right there, and it will be upside down, or sorry, not upside down, but much, 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 much reduced. Our converging image, which is real, is upside down, and this is par for the course with what we've seen in class. So use these three rules to help you generate your ray diagrams and get an idea as to what you should be finding. The real purpose of a ray diagram is not to solve for exact values, but it is to give you an understanding of what it is that you are supposed to find with our mathematical equations. Okay? So keep this in mind, and remember that the focal points are essentially flipped, and you should be perfectly fine. The rules are basically the same. They just have the focal points in different locations. If you have any questions, feel free to come see me in class or drop me a comment on YouTube, and I will see you next time. Converge to your goals.